All right, this is the last lecture for 127. I'm going to talk about protection mechanisms and demonstrate a couple projects. There will be a class next week, but I'll just help people. I'm not going to present any new material. And after that, the final exam is available online, just like your quizzes. So let's start with the chapter, which is here. All right, so we'll talk about these protection mechanisms, the non-executable stack, write or execute, and stack data protection. Quite a few things that have been used to prevent stack-based buffer overflows, which are the main form of attack we've done in this course and that people did historically. And we'll talk about heap protections and structured exception handler protections. So there are general protection mechanisms to try to make your system safer, even though you can't totally remove the vulnerability. And this is really important because a lot of people have custom code they wrote and their developers don't know how to write secure code, or they have a commercial app or some old app that was written by somebody else who didn't write it securely, and yet you would like to be safer even if you have to run an old version of some old app. So here's an example of C code. So you have a function and it defines an integer, a array of characters, and another integer, and so you see them here on the stack. And the buffer is here. It has room for 80 characters. So if you were able to put in more than 80 characters, it would start overflowing, and some of the letters fed into this variable would start changing this variable, and eventually it would hit the saved EBP and the saved return address. And when you hit the saved return address, then you get remote code execution. Now you can jump to any address you want, and the hacker can control the box. So one solution is non-executable stack. Now that doesn't stop this injection from working. But what it means is if I also try to inject my exploit on the stack here and I jump to it, it won't run because the stack is not executable. So this is available in all modern operating systems. You can still overwrite the return address and it will still control the instruction pointer, but you cannot get the instruction pointer to go to the code you injected because it'll be on the stack and it won't be executable. So there are various solutions. One is, of course, to put the shellcode in the data section, if you can do that. That might be executable. If the overflow is on the stack, you're going to have to find another way to place shellcode in memory. And one thing would be if you can get it to read it from some device and put it in I/O, then it would put data on the heap. That'd be one way to get the data somewhere other than the stack. You can use the return address to jump to a C library function. Now, when you jump to a C library function, it will expect to find parameters on the stack, but you can put those on there too. So you can make a call to any C library function with parameters of your choice. And one problem is you can't inject null bytes. So if the address to the function you need includes a null byte, you won't be able to use it. So for example, you can do stir copy. That's a C library function. It will copy a string from one address to another. So you can inject a parameter that points to your shellcode, and then a destination parameter that points to some area of memory that's writable and executable, and then it will return a pointer to the shellcode. So it looks like this. You inject data, any junk here, you overflow the buffer, you add extra junk here to get to the right place, then you put in the address of string copy, then you leave space for the return value, and you put parameters on the stack. It goes to stir copy, it finds the parameters on the stack, and it then returns the value here, which points to the new code it wrote, and that is then the next code on the stack. As it returns from that, it will go to this address and run that code. So it's pretty cute. And so return to gets is very similar. Instead of doing a copy of a string, which assumes you've already got your shellcode somewhere in there as a string variable, you call getS, which will read from the keyboard. So now if you have control of the input, if you can type key presses that go in the machine, or if you can somehow connect it to draw data from a file you control, then again, it's pretty much the same. You run getS, it sends you an address to where it put that data, and then you run that data. Return to code is another way. This is what we used here. You return to code that already exists in the application. C library is one place you can go. You can go to other places of code. When we did the Windows attack on Vuln server, we jumped into the Vuln server code itself. Found something in there we could use, I think. You can use anything, as long as you can find something and you can predict what address it's going to be at, so hopefully it's something that doesn't have ADSLR turned on. And you can have chain direct to code that has a series of calls to existing code, and so there's various techniques. You move the stack pointer to a buffer, and fix the stack pointer after each return, go into various functions. This is the beginning of ROP, return-oriented programming, where you just have a bunch of calls that add up to what you want. And you can return to syscall. Now, if you want to do this on Linux, then you're going to make a syscall right into kernel mode, which you can do, but you have to put the parameters in the registers, so you can't just put them on the stack. You're going to have to find code fragments that pop the arguments from the stack into the registers, so you'll have to have a chain, a ROP chain. It first goes to something that says pop stack into AX, return, then to something that says pop stack into EBX, return, until you get the right data in the registers, and then call it. You can do it, though. All right. And you can jump into the text section of the binary code where the program's code lives. And this is increasingly popular, as we're going to talk about. The defenses that are coming up make it hard to run any code that's not in the right section. But it must be possible to run the code in the text section, which is the code the developer put there. So if you can just reuse the developer's code for your malicious purpose, that would be the best. And you can jump to the procedure linkage table, which we did in the projects in the format string vulnerability, a series of pointers to libc functions, so you can go there and you can use functions, but you can only use functions that were called by the program. The others are not present in that table. You can jump to a dynamic linker resolver, and this will let you find functions that were not used by the target binary. It will hunt for them and connect to the libraries that are needed to find them. So that's cute. So a non-executable stack will still allow the return address to divert flow, because redirecting flow is just a matter of copying that address into the EIP. It's not executable, so it doesn't prevent you from executing code elsewhere if you can figure out where it is and find an address to it. So I'll demonstrate this one later, but we got a bit of stuff here. So here, ED303, I should have this ready to go. So let's take a look at mem.cpp, which is here. Okay, type mem.cpp. All right, so here's the function, and it's got some libraries. It doesn't really matter. And now I define a variable D to be in the data section, and I define a pointer here, and I have a buffer here, so the stack cookie protection will take effect. And then I just print out various addresses. I print out the address of something in a text section, data section, heap, and stack. And then I print out the top 10 words on the stack. So you can see them here. It's just a little bit like using a debugger. And so you compile with protections, and then you can see what happens here. So let me run this as CLS and mem. All right, and so I can just run this. You can see here, here's the text section, the data section, the heap. Just look at the top 4, and I'll just run the same thing a few times, and we'll see if they change. So the first one is always the same. The second one is not changing. Third one is changing. So the heap is moving around, and the stack is also moving around. So this is address space layout randomization. Each time I run it, it randomizes the location of the heap and the stack. All right, let me go to my slides. Okay, but text and data don't change. So this is a thing to realize. Not every segment of a program is randomized, which is interesting. All right, now if you compile it without protections by turning off dynamic base, then it will be even more unprotected. So that's mem2, I think, or memn. Let's see what it is. Memn, all right. All right. Oh, okay, let's do a directory and find out what it is. Mem1, I guess, all right. All right. So I can run this one several times, and it looks the same as the other. The heap and the stack change, but not the data and the text. But we can look at the stack and see what changes here. And all right, well, we'll get to that later. I'll demonstrate it when we get to the project. I think my demonstration here is not right. I probably have to recompile that. Anyway, we'll get to it later, so let's try Kahoot. All right. That's 14A, all right. I think we're all here now. All right, so which method is shellcode on the stack but executes it in a different memory segment? Yeah, return to string copy, that will copy it from the stack to some other memory segment. All right, which defense stops code on the stack from running? The non-executable bit, that's the point. All right, you can mark memory segments non-executable. Which method jumps directly to system? That's one of the C library functions, the one that runs a shell command. So that's what it is, it's return to libc. And which attack reads shellcode from the standard input? That's gets, of course. Gets reads from standard input. All right. So, write or execute. This is the modern way. Memory should be writable or executable. Each segment should obey this. You never let them both be true. Because if they were both true, then you could write data there and execute it. So you make the code section executable but not writable. So you cannot write self-modifying code, something I used to do decades ago. Your code can't be modified, and the stuff that's modified can't be run. This is the general plan, write or execute. So an early Linux implementation of this was considered secure, but it was cost too much performance, so it didn't become popular. The NX bit is the one that we have on Windows machines. They call it data execution prevention. And for client versions of Windows, it's only on for some critical Windows system files, and it's not on for other applications because too many people want to run old code. For servers, it's the opposite. It's on for everything unless you turn it off, because generally you don't want people running old vulnerable code on a server. So there are limitations. You could still use return to code using code that's already present. You just jump to code in an area that's executable. And that's the point. You can use return to code as long as you can find the code. Some memory might still allow it. All right. You could also write to disk and then execute the disk file, launching a process. There's a lot of ways to get around it. It's not perfect, but it does stop the simple, classic aleph null style buffer overflow attack where you inject code on the stack and run it on the stack. So you can also turn it off, of course. There's a single library call that will turn it off. This is often what you do, like I mentioned in the news. If you don't like the security software, you just bring the installer and turn it off. So that's the problem. There are ways you can turn it off, but you will have to inject null bytes, so that might not work depending on the nature of your exploit. You can also change the permissions. So the virtual protect is the library function that will change the permissions, so you can just change it to write plus execute. It's not like they've outlawed it and made it impossible to do. They've just made it not recommended, but there is an option to make writable and executable areas of memory. All right. And so another way, of course, is have two steps. First, make it writable and write to it, then change it to executable and execute it. If you can make library calls, you can do that. So, you can also create a new region of memory with both permissions turned on. All these are possible, the ways to work around it. All right, and so then you got to protect the data on the stack. Stack guard and pro police are ways to do it, also called stack smashing protector. And so stack guard originally only protected the return address. it left the EBP vulnerable. It would just detect you with a canary here if it's going to overwrite data to where it's going to hit the return address. That's the most important thing, but letting them modify the EBP is not a very good idea either. There may be ways to use that to move the execution where you want to go. The first canary was the null canary, because they think you won't be able to inject that, because you won't be able to inject all those null bytes. Then they changed it to the terminator canary, which has a whole bunch of bad characters. So even if you can write a null, you might not be able to write a carriage return or a line feed or an end of form character. These are things which would probably end whatever your input is. That was the idea. Now the popular one to put in is a random canary. All right, then another one is the ideal stack layout, and this tries to rearrange the variables so the buffers, the strings, are at the bottom. So if you overflow them, you're not going to hit as many other things. That's the idea. So here's the ideal stack layout. You put integer variables here, and you put the buffer at the bottom, and then put the canary right there. So if there's only one buffer, then you won't be able to overflow it at all without hitting the canary. Now, of course, if there's 2 or 3 string variables, you might be able to overflow from one string variable into another, and this won't save you. But that's not easy to take over the box with an attack like that. It's a lesser risk. They also make compromises. Apparently the cost of this is high. I was surprised. They don't protect all functions. They only guess which functions appear to have a buffer that might be overflowable and only protect them. So like I say, if you change several buffers, one could leak into another. And you can't, if you have a structure, a data structure, then it has a specific layout. Text, string, pointer or something, and it can't be rearranged by the compiler. It has to be in exactly that order. So that's a thing. It would be up to the developer to think about this when designing their structures, which they probably won't. And if you have functions with a variable number of arguments, then you can't put them in an ideal layout. So there are limitations like everything. I didn't know anybody ever did this. You know, alloc will reserve memory on the heap, but there's something called alloc A that will dynamically allocate memory on the stack. And if you do that, it's always at the top of the stack frame, where it would be most dangerous. So that's a thing to be aware if you use that. And of course, like I say, you might be able to find something located after the buffer, like the exception registration record, which is stored on the stack, which might let you use a structured exception handler exploit, and other variables that might be there. Even though you can overflow it only to a certain point and you can't hit the return pointer, you can still hit stuff, and for some programs, there might be something useful there. Another thing people tried was ASCII armored address space. You load all shared libraries in low memory, starting with null bytes. Therefore, you won't be able to inject the null bytes to use them. That's the idea. This is better on big endian architecture, where the null byte is at the start of the address, because then you won't even be able to inject an address, because you can inject one null byte at the end of your string. So if I only need to inject one address into a little endian system, I can do it, even if the high byte is null. Just once. But if it was big endian, then I wouldn't be able to inject the null to start the address. I wouldn't be able to inject any of the bytes after it that contain the address. So that would be better. But I don't know. I know Intel is little endian. I think ARM can be either way. Anyway, all right. So if you want to execute this Linux command, which will add a new user account to the system, you can still make one call to system by making the last injected byte the null. So that's the thing. All right. So if you want to defeat this thing, here's an example of it. Here's the call to system. This is the address to system, and it ends with a null, but I can still get there. I inject that one null right at the end. I still get to put it in. All right, and the main executable is not moved there, so you could use that code the way we did when we attacked vuln server. We didn't attack library functions, we attacked vuln server itself, and it's up in higher memory. So, you know, there's always, this is what you do. You make a defense, and the bad guys always find a way around the defense. So you make a certain generation of malware obsolete, but they just modify the malware to put around your defense, and that's the way it is. The cops get bigger guns, so the crooks get bigger guns. So the cops get bigger guns. That's the way it is. I mean, if you submit a talk to DEF CON, they will ask you, right in the talk proposal form, they say, okay, if this is an attack, what's the defense? And then what's the attack that gets over that? And if this is a defense, what's the attack that punches through it? And what's the stronger defense that would stop it? This is the way it always is. Anyway. All right. All right, so what defense is very secure but was never used in mainstream Linux? Patch. All right. Which defense puts shared code in low memory? It's ASCII armored address space. If you're injecting strings that are ASCII, then you won't be able to inject very much there because they all have null bytes in all the addresses. All right, what defense protects the return value but not the EBP? Wait a minute. Oh, that's right. That's correct. It did that. That was stack guard. All right. All right, and what defense causes code to stop when it hits a knob? Something we saw a few times in the projects. Can't execute a NOP, it must be NX. If you can't execute a NOP, you can't execute anything, so you have a region of memory that is not executable. Good. All right, let's go back here. Okay, so then ASLR, like I talked about, randomization. In the first place, not all code is randomized. In a 32-bit OS in particular, there was an issue, not such a big deal in 64-bit OS. In the 32-bit OS, there aren't really enough registers, so there's competition for them. And tying up a register, keeping track of where you are, is a performance hit. You can use return to gets, of course, where it's going to get data and put it somewhere, and you know where it put it. You can make the application supply the address to you. You can get it to leak an address for a variety of ways, like a format string or many other vulnerabilities. Linux Gate is a thing sort of like the procedure linkage table. It's a pointer used for system calls, and often it was placed at a fixed location in Linux distributions, so you could find it. So that's the thing. The obvious way to get around address-based layout randomization is to find something that is not randomized. And it turns out not everything is randomized for various reasons. The other thing, of course, is if the randomization is just not strong enough. The earliest version of it only had 8 bits of entropy. So then you could just run your attack 200 or 300 times and you get lucky. There are only 256 possible values. So that's a pretty obvious one. That was in Windows XP. And we'll see there's more defenses. And in fact, I was surprised to find that Windows 11 still has not improved it. What we're going to see in the project is if you just try 10,000 times, you'll find one that's not randomized. And that was true of Windows 10, and it's still true of Windows 11. When I Googled, they made it sound like Windows 11 had improved this, but in practice, it has not. which is very common for Microsoft. So, of course, all the areas move together typically in memory, just the base moves. So if you find a pointer from any of the code areas, you can use it to figure out where the other code areas are. So there's also might be able to find the addresses. If you're on a Linux system, there is in the file system, there's a memory map, PID map. So if you can read that, you can just find out where it is. And of course, like I say, brute forcing a 16-bit value is not impossible. Even a 24-bit value can be brute forced if you can do millions of attacks. If your service will let you do 1 million attacks, like keep restarting every time or whatever's necessary, sometimes that's possible. The beast and crime attack I was talking about in the cryptography class, think nothing of requiring like 100 billion guesses. So I mean, there are some attacks where you put up with that. So a format string, of course, would let you read the contents of RAM, so you can find the memory map or the address to something. There are RPC calls that leak memory addresses. If you have multi-threaded Windows applications, then every thread has to have the same address space. So if you find a mistake in any of the threads, that would be enough. And Unix often uses fork, but fork does not re-randomize the memory layout. So it's a thing to be aware of. All right. And then there's the heap. The heap, you can have overflows there. We talked about it. And so if you're able to overflow, say, the data from here and overwrite these pointers, then when you delete this one later, it will try to fix this pointer to point over here, but that's a write operation where it's going to write an address here, and you end up, by overflowing the data, you can control the address and the data that's written. You end up in control of an arbitrary write operation if there's a heap overflow and then there's a free, because it's trying to fix this pointer, but it's using data that came from you. So that's the issue. You don't get an execute directly, but you get a write, and you can use a write to overwrite something that will eventually go to the EIP and take over the box, and we've done that in the projects. So there is a thing called safe unlink, which instead of just freeing it that way, before it frees it, it checks to make sure the pointers are intact. So before I delete this, let's make sure if I hop forward and hop back, I end up here, and if I hop back and I hop forward, that makes sure that all these pointers are intact before freeing it. That's a good idea. That's safe unlink. And there's something, by the way, very similar in Cisco routers. There's a thing called check heaps that just hops through the whole heap from the start, hop, hop, hop to the end, and hop all the way back. And if it doesn't get back to where it should, it just restarts the router, throws away everything, says, oh, somebody's corrupted the heap. So that's one defense.
And then everything is randomized again?
Well, it is not, heap is not even necessarily random. But the point is it's intact. That means nobody's been overflowing it and changing those pointers. And Cisco routers, if anything bad happens, they just reboot the router, lose some packets, it doesn't matter, just get back. That's why they're often like running 20-year-old versions and crashing all the time, and nobody even notices or cares, because until they stop completely, the data still goes through. Yeah. All right. So safe unlink has been implemented in Windows for a long time, and also Linux. Not all heap operations are protected by it, however. Just like everything else, whenever there's a defense, it's not 100%, and there's a whole bunch of complicated ones in this website, Maleficarium. That's right, complicated heap exploits. There were a ton of them, so Microsoft has been adding new defenses. Right, so there's unsafe unlinking. You can overwrite the pointers carefully so it will pass that check. And then the pointers will still do desirable things. So that's one way. There's a thing called chunk on look-aside overwrite. There's a look-aside list that records free chunks, sort of like fragmentation of a disk. But they're not used in modern versions of Windows. Instead, they use something called a low fragmentation heap. This is a problem. As you keep making chunks and deleting chunks and making new chunks, after a while, your heap is a mess, and you can't find a nice contiguous block of stuff to work with. So you have to have something like defragmentation going on in the heap. So Windows XP started putting random cookie in each heap chunk's header. So just like a canary, it'll now detect if somebody's been overriding the data. All right. So that's a thing. All right, but it was only an 8-bit number. So again, you could just try 256 times until you get lucky, and the thing you inject is accepted. In Vista and later, it's 8 random bytes, and so that's a lot stronger. That's a lot harder to guess. That's 64 bits of randomized data that you aren't going to be able to predict or guess. So, and Windows 8 added even more protections, heap handle protection, and arbitrary free injection. They'd add a whole bunch more. And this is because Microsoft started a conference called the Blue Hat Conference, where they invite hackers to come visit them, and they will pay you a large pile of money if you find a new attack, and they'll pay you another large pile of money if you design a defense to stop it. So they started using the ethical hackers of the world to make all these clever defenses to stop heap attacks. So they're getting stronger in every version. So there's cookies in the kernel pool. They made the kernel pool non-executable, and supposedly much improved randomization, although I'm still not very impressed by it in practice. So randomization is a huge problem. To solve this, Intel started including a hardware random number generator in the chip, so you'd have genuine random numbers, but the problem is nobody trusts them because the Snowden revelations came out around this time, showing that the government had indeed pressured important security companies like RSA to lie about security and recommend people using unsafe stuff. So nobody trusts anybody. It proves that your conspiracy theories are correct. And so a lot of people won't use it anyway. The FreeBSD won't use it, assuming it must be poisoned. Windows 10 adds even more defenses, just lots of them. An anti-secure boot was supposed to stop the bootkits we talked about in previous classes, I think in malware class. And you've got trusted boot that verifies it on boot up and improvements to address space layout randomization and data execution prevention, although I don't notice them, as we're going to see. All right, and just a lot of more things. Enhanced protected mode in the browser. And in BSD, they had an older malloc to reserve heap data, which didn't use linked lists, but now they use mmap, which gives you randomly located chunks of RAM in the heap, and no two chunks can ever be adjacent. So this would make it more difficult to overflow and hit the next one, although not impossible, but it would give you a sort of random defense against it. So overriding control structures in the heap are getting harder and harder. Now, of course, you still have the old-fashioned thing. There are two chunks of data in the heap, and you just want to modify the second one. And that's, of course, hard. None of these defenses will stop you from doing that. Those don't give you arbitrary control of the box, but they might let you do something depending on how the program is laid out and how it uses the memory. Like the first one we did in this class, they put a pointer right after the buffer. So all you had to do is overflow into the pointer, and now you're controlling something that will be used to control code execution. So you might get lucky sometimes and have something good right there in the heap chunk, where you don't even have to overflow the whole heap chunk to get something good. But that's going to be rare and depend on the details of the program. And then there's the structured exception handler. Before Windows XP Service Pack 1, the EBX would always return a pointer to the SEH. So it totally overcame all these defenses. You could find it. So they fixed that. Now the registers are zeroed before you go there. And the exception handler can't be placed in the stack. So you can't inject code on the stack and jump to it with an exception anymore. And if you compile with safe SEH, which we talked about in the projects, then it uses a whitelist, which we call an allow list these days, of permitted exception handlers, and all the rest of the code can't be used. So this blocks things that would redirect the exception handler to go somewhere else. You can only go to the official handlers. And however, some memory sections are not compiled with this, and there are some exploitation tools to help you inspect the SEH and see what's there. And you can do some of it just with Mona, which we did inside Immunity, to see which of these defenses are turned on for different memory segments. All right, so let's do the last Kahoot. All right, which one is a defense against heap overflows? Safe unlink. Prevents, it's like a canary. It prevents you, the overflow still happens, but it prevents you from taking the action that would cause the overflow to give the attacker control of the box. All right, which attack bypasses ASLR by letting you specify where to put the shell code? That's gets. Gets reads data and then puts it where you tell it to put it. One of the parameters is where do you want me to put that data? All right. All right, which one exploits the SEH? That's EE-REAP. It's one of those attack tools I mentioned briefly. All right, and how many guesses will it take to find two independent random 8-bit values? $65,000. 256 will guess one, but you need 256 squared to guess two of them. So if you have a 16-bit random value, you'll have to guess 65,000 times to hit it. Approximately, of course.